Okay, so this next video we're just going to start up on the definition slide. This is slide 17 in the PowerPoint notes. You should have already added these into your notes and read through them, but let's talk about some of these really quick. And by the way, when I say definitions are important, that's because a lot of the time you'll see questions on the IB exam having to do with definitions, and you basically need to know these definitions word for word. So, internal energy is the total kinetic energy of all the atoms making up an object plus the internal potential energy of those atoms. Okay, now please do not forget the word atoms. This is crucial to the whole thing. This is not the same thing as mechanical energy, right? If we take a ball and we lift it off of the ground and then we throw it through the air, it has kinetic energy and potential energy. Okay, that has nothing to do with internal energy. Internal energy has to do with the energy of the atoms making up the object. Okay, the total kinetic energy of all the atoms making up an object plus the internal potential energy of those atoms. Okay, so please don't forget what we're talking about there. Temperature we've talked about before. Notice, by the way, in the notes it says temperature is a quantitative measure of the average kinetic energy of the molecules or atoms making up an object. Quantitative just means with numbers. Now, temperature does not have units of energy. Okay, so temperature is not equal to this, but it is a measure of this. Pressure, a quantitative measure of how frequently these molecules or atoms collide with their container walls. So we've talked about those in the last video. Heat is new. Now, for reasons I don't understand, heat is typically, the symbol for heat is typically written as a capital Q. The unit for heat is joule, and the reason it's measured in joules is because if you look at the definition, heat is the transfer or flow of energy between two objects. Now, if you're thinking about that closely, you might think, wait, isn't that the same thing as work? Well, heat is the transfer or flow of, let's say, thermal energy between two objects. Okay, let me add that word thermal in. Okay, measured in joules. And heat tends to flow from hotter objects to colder objects. Thermal equilibrium, this is a very important term that we'll see. By definition, two objects are in thermal equilibrium when you put them in thermal contact with each other and they reach the same temperature and there's no net heat flow between. Now, what does that mean? Well, if you imagine, for example, let's say you take a spoon and you put it in the freezer. Okay, you make it cold. Okay, if you wait long enough, the spoon, which was originally at room temperature, is going to reach the same temperature as the freezer. Okay, in other words, if you have two objects in contact for a long enough period of time, they're going to reach a point where there's no net heat flow between them. Right? Heat tends to flow from hotter objects to colder objects, from temperatures or from higher temperatures to lower temperatures. And so eventually what's going to happen is the freezer is going to warm up a little bit, the spoon is going to cool down a little bit, and eventually they're going to reach the same temperature. Okay, if you take the spoon and you put it in a cup of water, okay, eventually what's going to happen is heat is going to transfer from the cup of water into the spoon, because the water is warmer than the spoon. And if you wait long enough, they're going to reach thermal equilibrium. And just to show you what that looks like in a simulation really quickly, here I've got two objects. I've got a block on the left that's 10 degrees Celsius and a block on the right that's 40 degrees Celsius. And they are currently touching each other. They're in thermal contact. Heat is going to flow from the right to the left for the most part until they reach thermal equilibrium. And this can take a few minutes. And so let's see what that looks like. Okay, so here we see that heat being transferred. This object is cooling down. This one is warming up. Over here we can see the temperature of the objects kind of converging. And eventually, right about almost right about here, they're going to reach thermal equilibrium. And now they're at the same temperature and there's no net heat flow between them. Okay, and so that's what is meant by thermal equilibrium. And then phase change. Phase change is just what you call what happens when a substance transforms from one state of matter to another. So for example, melting is a phase change. Going from a solid to a liquid is a phase change. just a few more notes over definitions. This one we talked about before. Now, you've got kinetic energy, which obviously has to do with motion. We talked about that before. And we know that in all objects, the atoms and or molecules are at least vibrating, if not like actually flying around. So clearly they have kinetic energy. The potential energy, we're not going to go into a lot of detail about the potential energy, but basically it has to do with electrical forces between the atoms, because atoms are made of charged particles and they can attract or repel each other based off of electrical forces. We're not going to really talk about that, but it does kind of have to do with the different states of matter. Make sure that you don't confuse heat and temperature. Heat is not something that can be possessed because it's the transfer of thermal energy. Just like work, you cannot possess work, but you can do work on an object if you transfer energy to or from the object. Heat is the same thing. And temperature, we've already kind of talked about that. If you read through this slide and add this slide to your notes, you'll see that for the most part, we've talked about these things already. We've already looked at the simulations and whatnot, so I don't want to spend too much time on that. And again, these are things that you can, add to your notes and not add to your notes. Actually, now that I look at them, I would definitely add these to your notes, especially the last sentence of each of these things. Okay, that is important. You should change this to ideal gases because this is only true for an ideal gas, and we'll talk more about that later. So take a moment to add these things to your notes. Okay. States of matter, this is just showing the different ways to transform, to have phase changes, melting, freezing, evaporation, condensation, things you should already know. By the way, do keep in mind, melting and freezing are basically the exact same thing, just in opposite directions. So later when we talk about like the melting temperature of something, the melting temperature and the freezing temperature are going to be the same number, right? So let's talk about temperature scales. Okay, so there's 3 temperature scales that we'll talk about just kind of briefly, keeping in mind we're mainly going to be working with Celsius and Kelvin. Fahrenheit we're only going to talk about just so you can use that as a reference because the Fahrenheit scale is commonly used in the United States, and so that's probably what you can relate to the most. On the Fahrenheit scale, 32 degrees Fahrenheit is the freezing point of water, or if you prefer, the melting point of ice, and 212 degrees is the boiling point of water. Now, if that seems kind of random to you, it kind of is, actually, which is why it's strange that we use Fahrenheit and we don't use Celsius like the rest of the world does. Celsius, the way it's defined, makes a little bit more sense. The Celsius temperature scale is a temperature scale which defines 0 degrees Celsius as the freezing point of water, and 100 degrees Celsius as the boiling point of water. Those are values that you have to know, by the way. Now, if we want to convert between Celsius and Fahrenheit, there is an equation for that. And the equation basically looks like this, and I'm going to write it out really quick, actually. Okay, so the temperature in Fahrenheit, actually that should be a capital F, is equal to 9/5 times the temperature in Celsius plus 32. Okay, so using this equation, you can convert from Fahrenheit to Celsius, and we'll do an example in just a second. Okay, but just, to give you a quick example, let's say you've got 0 degrees Celsius. 0 degrees Celsius. If I plug 0 in for Tc, I get 9/5 times 0 plus 32. And so I get Tf equals 32 degrees Fahrenheit. In other words, 0 degrees Celsius is the same as 32 degrees Fahrenheit. That is the melting point of ice, or the freezing point of water, if you prefer. Okay, so that's mainly for your own reference. I said before we're primarily going to be working in Celsius and Kelvin, but we will do a few conversion problems in a second. Kelvin is the SI unit for temperature. The Kelvin is defined as 1/273.16 of the thermodynamic temperature of the triple point of water. Now that's kind of a wordy definition. I don't know if you need to know the definition of Kelvin anymore. It did used to be in the IB curriculum, but I think they've taken that out. You might ask, though, what is triple point? And so that's something we'll talk about at the end of this video. This is kind of an interesting little phenomenon. This relationship is given to you on the IB exam, but just so you know it, to convert between Celsius and Kelvin, the equation looks like this. You take the temperature in Celsius and you add 273.15, and that gives you the temperature in Kelvin. Now, if you leave off the 0.15, it's not that crucial. It's not the end of the world, but technically it should be there. Okay, so what we're going to do now is we're just going to do a few examples with unit conversions really quickly, and then we're going to talk just briefly about the triple point concept. So let's do some basic temperature conversions. Example 1, convert 45 degrees Fahrenheit into degrees Celsius and Kelvin. By the way, you don't typically say degrees Kelvin, you just say Kelvin. So if we have a temperature of 45 degrees Fahrenheit and we want to relate that to Celsius, then the first thing we're going to do, I'm just going to write down my given, TF is equal to, what is that, 45 degrees Fahrenheit. And we want to know what is TC and what is TK. Okay, well, I don't have an equation that lets me go from Fahrenheit to Kelvin. I mean, I could make one if I wanted to, but that's not what I'm given. So the first thing I'm going to do is I'm going to find the temperature in Celsius. I know that the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. And so I'm going to solve this using the magic of algebra. So why don't you pause here and check to see if you get the correct answer. Okay, so we are going to subtract 32 on both sides. We get 9/5 times TC. So that's going to be 45 minus 32 equals 9 TC/5. That's a 5, by the way. Okay, so what is that? That is 13 equals 9 TC/5. And then I'm just going to multiply the 5 up and divide by the 9. And so you should get TC is equal to 7.2 degrees Celsius. Okay, just a real basic unit conversion there using the equation, 7.2 degrees Celsius. Okay, so I'm going to erase just a second. Actually, okay, so now that I have the 7.2 degrees Celsius, I can easily go back and find the temperature in Kelvin. Okay, the temperature in Kelvin is the temperature in Celsius plus 273.15. So the temperature in Kelvin would be 7.2 plus 273.15. And so the temperature in Kelvin would be equal to 280.4 Kelvin. And again, Kelvin, not degrees, Kelvin. It should be a capital K, by the way. Okay, so when you see a problem dealing with, 280 Kelvin, just to put that into perspective, it's about 45 degrees Fahrenheit. Okay, so I'm going to clear the screen. And we'll just do one more quick example. Example 2, convert 300 Kelvin into Celsius and Fahrenheit. So we have TK equals 300 Kelvin. And this is really basic stuff. But I just want to make sure, number one, you can do these conversions, and number two, you kind of have a feel for what these temperatures represent, so that if you're doing a problem and you get like 5,000 Kelvin, you realize what that means exactly. So the first thing we're going to do is go from Kelvin to Celsius. All I'm going to do is I'm going to take my equation and I'm going to plug in and solve. Okay, so this should be a very easy calculation. TC is going to be 300 minus 273.15. That should be, and I'm just going to round, 26.9 degrees Celsius. I just rounded to 1 decimal place. Okay, now once I have TC, I can go back up here to my my Fahrenheit equation, do 9/5 times 26.9 plus 32, and I plug that into my calculator, and the answer I get is somewhere around 80.3 degrees Fahrenheit. So you might want to check the answer on your own. But there you go. Okay, so if you're doing a problem and it talks about 300 Kelvin, that's about 80 degrees Fahrenheit. So a little past room temperature, but still not too warm or anything. Okay, so those are just some really basic unit conversion problems. Hopefully not anything that would give you too much trouble. So the last thing we're going to talk about is something called triple point. And I want you to watch these videos. This is slide 26 in the PowerPoint notes. I want you to watch these videos. Basically, I'll tell you what triple point is. If we go back to our simulation, then what I'm going to show you, I'm going to reset this. If you look down here, there's something called a phase diagram. And a phase diagram basically shows pressure on the y-axis and temperature on the x-axis. And notice that in this region of the graph you have a solid, in this region of the graph you have a liquid, and down here you have a gas. Okay, and so what is meant by triple point is basically this point right here where those three sectors kind of overlap. In other words, at the triple point, you kind of have a mixture of a solid, liquid, and gas all at the same time. Okay, and it's a really cool thing to see. I would definitely encourage you to watch these videos and to go on YouTube and Google triple point on your own and see some examples of what that looks like. It looks really, really cool, and I want to make sure that you experience that. So go to YouTube, check out those videos. We're going to stop the video here, and then we'll pick up with specific heat capacity in the next video.